I'm basically here to talk about the CERT C++ secure coding standard, which is right here, establishing safety or coding requirements for non-safety critical C++ systems. A rather long title. It's important because there are lots of safety critical C++ coding standards, but ours is in particular a non-safety critical. So I think it's pretty uncontroversial to point out that secure coding in, well, just about every language is hard. It's especially hard in C++ because the language is so big. It is a superset of C, and we already have a coding standard in C, but we haven't had anything to deal with modern C++. There are other standards in C++. I'm showing you that the JSF++, Joint Strike Force, and MISRA both have coding standards for C++. However, these are particularly designed for safety rather than security. So they are suitable for embedded programs where safety is critical. They're not suitable for your enterprise server or even your Android app or your Windows program. So they're also fairly old, from 2005 and 2008, and the C++ language has evolved a good bit since then. In 2011, the ISO committee released a new version of C++ with many new features. Lambdas, concurrency, move operators, and lots of other fancy features are now in the language, and those old standards don't cover them at all. So one of our goals was to address these new features in C++ that helps to make the language a lot more powerful, and they also help with security. There is a third standard that I'd like to bring up, the C++ core guidelines, which is also available on the web. But there's two differences between them and us. What they make are generally good ideas for the language, but not hard and fast rules. For instance, they have a guideline saying don't use do statements. If you're writing a new C++ program, not using do statements is a good idea. But if you already have a huge legacy code base, it might be perfectly secure and still use do statements. We are not going to tell you not to change your code just to take out the do statements, because they're not necessarily the cause of problems. So to summarize, the goals for our standard was to be up to date, to apply to all C++ code, not just the safety critical code. We also made a conscious decision not to duplicate rules that are in the C standard, the C secure coding standard. We already have a perfectly good C secure coding standard, and why not leverage that and simply declare that some of these C rules apply as well to C++ code. Finally, in addition to the rules, we wanted to write some static analysis checkers that would enforce these rules. The goal being to prove that the rules were enforceable, that some of the rules were enforceable statically. We would write enough checkers to prove that the rules were good. I should add that enforceability was a goal of our rules. However, there's two different levels of enforceability that we strive for. The first is manually enforceable. If you look at the rule and you look at some C++ code, you should be able to, two programmers can agree on whether or not the code violates the rule. If the two programmers can't agree and they both understand the code, then the rule is probably rather poorly defined and can use some refinement. But all of our rules are supposed to be manually enforceable by manual analysis. There's a higher level of enforceability, automatic enforceability by a static analysis tool, and we strive for automatic enforceability in our rules. We don't always achieve it. There are some rules that are simply not enforceable at compile time. A good example would be the rule against dereferencing null pointers. Every standard I know has that rule, but you can't check it statically without the danger of false positives. So I'm first going to talk about what we accomplished, the impact and the checkers, and then I'll talk about the rules themselves and what they look like, and finally I'll go a little bit into our process of how we built the rules. So our checkers, the result was that we created 15 checkers
using the Clang compiler front end to LLVM. So Clang is actually an up-and-rising star in compiler technology. Quick question, how many people here are using Apple products? Macs, iPhones? Couple people. So if you're using an Apple product, then its software was built using Clang. Clang is the primary compiler in the Apple world. It's also supported by Visual Studio and Linux. So it's used by an awful lot of, tens of millions of programmers. So it's open source, and that means that checkers that we write that get accepted into Clang will eventually be used by all those Apple programmers and by people who use them in Visual Studio or Linux as well. So these checkers should have some major impact. In addition to our 15 checkers, that's only a small subset of the rules we have, but the Clang community has expressed interest in writing more checkers. I suspect that if we completely drop the project, they would continue to write checkers to support our rules. So we would like to continue with the project and shepherd the new checkers so that they adequately enforce the remainder of our rules. So this is a good bar graph showing what rules we have for both the C standard, which already existed, and the C++ standard, which is now nearing completion. The blue part of the graph represents rules that existed before this fiscal year. The yellow part represents rules that are new for this fiscal year, and the green represents the C rules that we judge to be inapplicable for C++. C++, as I said, is a superset of C, but there are some differences, and that alters the strategy by which you should conform to secure coding practices. So a lot of those rules we simply overrode in C++, saying, don't follow those rules, follow this rule instead. As you see, we added about 15 new C++ rules and 2 new C rules, and we pretty much modified all of the pre-existing C++ rules. So there's actually a lot of work. Finally, the chapters, we organized all of our standard rules into sections or chapters. The chapters for C++ you see on the right here, and they are pretty close to the chapters for the C standard. There are a few differences, such as since C has no exceptions, its chapter is called error handling, and C++ has a chapter called exceptions and error handling. C++ also has object-oriented programming, a chapter completely missing from the C standard. But ultimately, we have a total of about 83 rules in C++, along with, I believe, 79 C rules that also apply, which make for a pretty hefty standard. Okay, so I'm going to dive into one particular rule here. This is rule DCL 22-CPP. That stands for declarations. It's a rule about declarations and initialization, and it is a C++ rule. Every rule begins with this kind of ID, which is very easy to Google. If you just type that into Google, you should get this web page right now, publicly on our wiki. Along with the ID, the rule has a concise, but not necessarily precise title dictating, what the rule is about. And then following the title is this introductory text, which gives background why the rule exists. And there'll be often some, quotes, perhaps from the C++ standard, supporting the rule and, justifying it. Following each introduction, there will be a set of code examples that, first of all, there'll be at least one, but usually more, non-compliant code examples, always circled with a, it's supposed to be a red box. I guess it looks kind of pink here.
Fails to comply with the rule, that specifically violates the rule and can therefore lead to unpredictable, unexpected behavior. Sometimes, something as bad as remote code execution. The text around the rule will explain why, and ultimately this is code that you should not be cutting and pasting. Don't try this at home. Following each non-compliant code example will be one or two compliant solutions that mitigate the problem in the non-compliant code example. They always strive for the same goal. They try to do the same thing, but they comply with this rule. In fact, they comply with all of our rules, and so the blue examples are code that you definitely should cut and paste and use in your own coding projects. So it is our hope that the non-compliant examples and compliant solutions give a full illustration of what we forbid and what we permit, and how to work around, the limitations the rule imposes. So after the code examples, you have a couple of sections like the risk assessment, which covers several simple metrics, such as the severity, that is the consequences of violating the rule, the likelihood the rule is that the violation of the rule yields a exploitable vulnerability, the remediation cost, how expensive is it to modify your code to comply with the rule. After the risk assessment, we have a section on automated detection. In this case, this rule can be automatically detected by Clang. I think this is one of the checkers we wrote. But we will also list, commercial and open source static analysis tools that can detect this violations of this particular rule. We had this for every rule. In this case, there's only one tool, but many rules will have multiple tools. Following that, we'll have related vulnerabilities. If there are any publicly documented vulnerabilities that came because someone didn't follow this rule. Then a related guidelines section, which will showcase related rules in the C++ standard. It will also show analogous rules in the C standard or the Java standard, and it can go outside CERT. We might link to CWEs, MISRA guidelines, whatever other things that we recognize as being relevant to this particular coding rule. And finally, a bibliography. This one just happens to reference the C++ standard, but we might reference other authoritative sources. So having gone over the checkers that we produced and the 160 rules, 80 in C and 80 in C++, I'll quickly talk about our process that we followed in order to produce these rules before then opening up to questions. So the process for creating these rules, first of all, there's plenty of sources to gather rules from. Probably the best source is the C++ standard itself. The standard doesn't speak about security, but it often speaks of undefined behavior, which is basically the committee's way of saying, if you do this in your code, then we're not responsible for what happens. Usually that means, dragons be here. Don't do this. And usually when we see undefined behavior, that's our signal that, there's probably a rule in here. Not only the C++ standard, but we've been attending the standards committee meetings and, helping to improve the C++ standard. Aaron Ballman, the PI, has been our C++ delegate for several years, and I've been his alternate. There's, in addition to the standard and the committee, then there's plenty of literature, books about proper C++ programming techniques, and other guidelines like the MISRA guidelines, the JSF, the C++ core rules. So anyway, there's clearly a large bounty of sources for C++ coding rules. When we discover something that would probably make a good rule, then we spec it out. We write it up on our publicly available wiki. You can see the work we're doing right now. And in fact, if you go to the wiki, you can see various comments that Aaron and I have left for each other on the rules. So as we spec out the rules, we've discovered that once we have a rule that's spec'd out, such as this example about using set jump or long jump, if the rule can be automatically checked, we will try and write a checker for it. So as you see in the black text there, we actually have a static analysis checker in Clang that will holler if you actually violate this rule in your code. And that's the output you'll get. Sometimes when we write the checker, we will discover that our rule was inadequate. Maybe it didn't cover all the things it should cover. Then again, maybe it had too many false positives, and we have to restrict it a bit. So basically, the rule helps to improve the checker helps to improve the rule, and you get, I think that's what synergy is. Not quite sure. Hopefully, eventually we reach equilibrium where we have a good rule, we have a good checker, and life then becomes unicorns and rainbows. Okay, so I've told you about our process, about our rules, and about our checkers. I'd like to open up to questions.